Either get excited for OES or ionized for mass spectrometry. Okay. And it generates an emission spectra, but you want the internal standard analyte you add to do things similarly, these things similarly to what your analyte does. And in fact, that's the assumption. The assumption is that it does. Okay. It behaves similarly. So you have some analyte, and so for the OES, they typically use, I think what he uses, I'll tell you tomorrow. I think he's using scandium and yttrium. So what's he talking about for yttrium? You guys are chemists. Everybody in here is a chemist.
That's right.
YT? Yeah. Okay. So, I don't know, that doesn't look right to me, but good. So I think he uses scandium and yttrium. These are unusual actinides, I think, right? Or something, one of them is, at least, right? Elements. That the idea is that one of them is relatively intermediate atomic mass. I think the atomic number of scandium is probably in the, you guys look it up, don't know what it is. 40s and 50s.
Y.
What?
It's just Y.
Okay. What's the atomic number for scandium?
21.
21. So it's its atomic mass is what?
44.96.
So let's say 45. Okay. And yttrium is
39.
39. Okay, so it's like 80 or whatever.
Yeah, 88.
88. Okay. Okay. So he has these two, and the beauty is he has on the instrument, he has a peritonic pump thing that has two tubes going through it. One tube is coming from your sample bottle, your vial. The other tube is coming from a bottle filled with these two analytes, scanning yttrium. And they're being pumped in and mixed together into the instrument at the same rate. And the concentration of yttrium scanning is exactly the same for all the samples and standards. It's pumped into the same rate for all your samples. And so the composition of these two internal standards that gets mixed with your sample that gets introduced to the instrument doesn't change over the entire analysis time. And so then you assume that there's something changing from one sample to another because of the matrix, and I get less ionization or less excitation of my analyte of interest because there's a lot more stuff in there, then the same thing will happen to my internal standards. And if I normalize the number of counts per second, the signal that I get from my emission spectra from my sample, and normalize it to this, if these go down, they go down, but if I normalize them together, we get the same signal, right? And so I can have a signal, if I'm measuring these two things, where maybe it's going down, the matrix or whatever, and the scandium and yttrium is doing the same thing. If I normalize my sample to the internal standard, then I can correct for that effect. And it's an extraordinarily powerful approach because it allows me to skip doing the method of additions, assuming that these assumptions are met. And it allows me then to just normalize computationally all the signal I get from my analyte to what's in there, and I can correct, in principle, correct for all these problems of pump noise, delivery, differences in delivery rate because some samples may be more viscous than others that get pumped and introduced into the plasma, and excitation and ionization process. It allows me to automatically, the instrument does it for me, correct for all that. And it's so much more effective than doing, and time efficient than doing some of these other approaches that we would otherwise have to do, like method of additions or something like that. And so all ICP kinds of instruments, whether it be OES or mass spectrometry, and even molecular mass spectrometry, most of them now rely on some technology that utilizes an internal standard approach. For mass spectrometry, we're going to talk about that later today or on Friday, the instrument's not set up to add it for us automatically like it does in the OES. We have to add it to each sample individually. And we add the exact same amount of some different internal standard, depending on what elements we're measuring, to each of our samples, so the concentration is the same in all our samples. And then if the concentration, the counts I measure in the instrument vary from one sample to the other, I know it's not because I messed up, I hope, and added different amounts, it's because there are different extents of ionization or excitation, and I can adjust for that. So that's what we do, that's what you will do in the OES. So what are they? Internal standards are one or more analytes that are not present in your sample, because if they were, it'd be a problem. Because if they vary from one sample to the other, then you get fluctuation in your internal standard that was not due to changes in the instrument sensitivity or whatever. they're not present in your sample, or they're present in very low levels. What's very low? To me would be like less than 1%. Right? So if it naturally occurs in your sample, you're going to be adding so much more that you're increasing it at least by 100-fold. Right? So therefore, fluctuations, natural fluctuations of that analyte in your sample will be negligible in terms of the variability that you measure. Does that make sense? Yes? Okay. That's one. And the other is, and this is important, and this is an assumption, that it behaves in the sample just like my analyte of interest. It's introduced, and ionides are excited, all these things behave the same way. And this is a huge assumption that oftentimes is not true. And it becomes, how far can we deviate from that and still be okay? There's some analytes that behave very differently from each other. And we have to, and it's a process for matching which internal standards would I use to match to my analyte. Depending on which analytes I use a particular internal standard. So for you, measuring transition metals, most of you, that's why scandium's there, right? But if you're measuring much heavier elements, like lead, then we use yttrium. The elements like yttrium. All right. So if I put all this on a quiz, now if we know what we know, you'd be like, I've got this, right? And it's such a fundamental approach in analytical sciences that I want to make sure that it's clear to everybody. There's no question about what it is and why it works the way it is. You have a question?
So it actually eliminates the need to do a method of additions?
Yes. If it behaves like you hope it behaves. All right, so you guys have worked so hard, do all this work in the lab, and it's sort of, it's high labor, low reward for what you've done so far. And you'll see when you start doing things in the methods like OES, is you'll go in with 20 samples, and you'll sit there, and the instrument does everything for you. And, in an hour, you'll get data for 50 elements. And you'd be like, oh, this is awesome. This is so faster and efficient than what I've been used to. And people have worked hard to develop technologies around this. Okay, so this is what this thing looks like. So the instrument you're going to use, you'll see tomorrow and Thursday, is it's a made by PerkinElmer. I think it's just Optima, blah, blah, blah. And we talked a lot about this, and they market this as a very, commercially it's a very popular, common kind of instrument because of the analytical capabilities for measuring a host of, nearly not the entire periodic chart, but much of it, right? And the benefit is that you can measure many things at once, which is hugely efficient, especially for those of you who may use Flame A, where you're going to do things one at a time, right? You can measure many things at once. You can measure multiple wavelengths per element. And so for one atom, like sodium in this case, that you're going to get multiple emission spectra from that, depending on what excited orbital electrons are falling back down to the ground state. And you can measure the emission spectra simultaneously. So you can measure 3 different emission lines for sodium. And you can calculate the concentration of sodium atoms compared to your standards from each of these emission lines and then see how well they agree. And then you can average across all 3 emission lines. So in principle, you are getting a more accurate representation of what the analyte concentration is because each emission line sometimes will have their own characteristics and some susceptibility to peak broadening and interferences. And you can measure multiple ones for each element to help combat that, right? You have the simultaneous injection of internal standard, I just talked about that, right? And so it helps account for changes in sample matrix. We just talked about that. And changes in fluctuation. Essentially, it's how important that is, right? It's got a special, this is not really important to us, but it's got a special, they've developed these different kinds of nebulizers. They call this one a Mira-Mist nebulizer. And they've got multiple generations of this. And the idea is that when you look at nebulizers, it seems like such a simple thing. But the goal of a nebulizer is to take your liquid and have it be aerosolized into very small droplets. And so on one hand, the way to do that is to have a nebulizer that has a really fine tip. So when you have your sample coming in here, the finer this tip, meaning the smaller that diameter, the greater the flow of gas coming out of that, and it creates more turbulence here that creates finer droplets of your sample. That's good. That's what you want. The downside is the finer the tip here, the more likely it is that as your samples come out here and start to evaporate in that gas, that if they have a lot of dissolved solvents, it gets clogged with crap. And that's bad, because then it gets plugged up, and that commonly happens. And so they develop these nebulizers to sort of maximize maximize the aerosolization of your sample and minimize the potential that it gets deposits of sample solids and it gets clogged up. And that's one thing that this thing has. But probably the most, I think, important aspect of these instruments, the technology that's been developed in the last 15 years or 20 years or whatever, is that they're fitted with these charge-coupled device detectors. And they're not just, they're not the crappy kind of CCDs you have in your phone camera. These are ones that have extremely high pixel resolution so that you can actually measure the broadening of your emission peak, right, at individual pixel positions on the detector, which is what this is reflecting here. So at one selected wavelength of, say, 490.033, you would get a distribution of the emission photons coming from your analyzer. Along those pixels of the detector, it would give you, ideally, a Gaussian distribution, which is what you'd expect, like this. So it allows you then to select and minimize any potential slight overlap you may have with adjacent emission lines by doing that. Which is very, very effective. And you can measure things across an enormous range of wavelengths, unlike what you see in UV. So, charge-coupled devices, people know kind of how those work? Anybody in here engineer? Anybody an engineer, electrical engineer? The way these work is, this is sort of a cross-section of what this would be. Charge-coupled devices, all of them work by the concept that they have a photoactive surface, meaning that when photons hit that photoactive surface, they generate a release of electrons. That's essential for all CCD detectors. And so when photons hit, and this is another characterization of it, when photons hit that photoactive surface, that photoactive surface and the absorption of that photon releases an electron. And what makes this special in charge-coupled devices is that they can have an array of these photoactive surfaces at very small resolution, right, down to the micron or nanometer size. And when those photons hit, they release electrons. Those electrons are transferred over into a register where those electrons will build up until they trip essentially an overflow gate, and then they get transferred to another register. And they can actually store electrons as the photons are hitting the surface until they reach a certain buildup of electrons, and it trips a gate, and those electrons will then flow to an adjacent register and be measured, and ultimately be measured. Okay. And so you would have a surface, kind of like this, right? But it's a surface like this. In that case, in the instrument, it's probably about that big. But it's got all these divisions of pixels of this charge-coupled device, and each of these pixels areas is a configuration like this. And the photons come in and hit it, and they cause a release of electrons into an adjacent register, and they build up there until there's a sufficient charge of buildup of charge, of separation of charge of electrons. And they transfer those electrons into a register that then ultimately get passed into an amplifier and amplify the signal. So you can think of it like literally a map of pixels on a screen that are each capable in each pixel position of collecting photons and generating an electrical potential, which is what they do. That's everything same. So the instrument, what happens is you essentially take the emission spectra, and it goes through a grading, an echelon grading, just like the diffraction grading we talked about. It splits those wavelengths, and it pinches those wavelengths on the detector, and in the software, it takes all that information and portrays it in a way that you can utilize to make decisions about things. So, Flame AA is pretty simple. You got a 10-minute demonstration by the TA, right? By Mr. Taylor, maybe 15-minute max, and you did it. And that's one of the beauties about Flame AA. The same with UV Viz. You can walk in, be naive to that technology, and within 10 or 15 minutes, you can be making measurements. How long did it take you to finally figure out how to make measurements on the iron competitor? Aside from just injecting it in the button, but if you had to do it, walk in and do it, it takes you a little bit longer, right? And it takes you longer largely because the software interface has multiple components and modules that you have to figure out how to navigate to set all the settings that you need to set. Opposed to potential to the suppressor, blah, blah, blah. Well, the OES and these kinds of instruments are notches a little bit above that, and what makes this complicated, and the reason I discourage people from using the ICP-MS spectrometer is that it's even more complicated, is because it's impossible for somebody to walk in with samples and spend even an hour to the point of doing the measurements because of all the different things that have to be dialed in. So in the case of the OES, what happens is you would come in, and Rob will do this for you, those people do that, is he would start pumping in some, they call it a tuning standard, some solution that has known concentrations of a bunch of different elements. And then you go up to the software pages and he starts selecting the wavelengths he wants to look at, and you want to look at. So you're going to go in and say, I want to look at iron and zinc and lead and copper and whatever. And then he'll say, all right, you tell the software that, and it says for copper, it recommends these 3 emission wavelengths, for lead, these 2 emission wavelengths, and for zinc, blah, blah, blah. So he'll select 8 or 10 different wavelengths, emission wavelengths to monitor, plus the wavelengths for scandium and yttrium. And then he'll go, while he's pumping that solution, he'll look at the intensity, the photon intensity coming from your analytes, the emission, and they show up as intensity on a pixel, particular pixels on the CCD array. So this is an array of pixels. In this case, it's 180 pixels, I think it says. 180 pixels or 170 pixels. That's the density of pixels within the area of the detector that the photons, 420.063 nanometers, will be hitting. Okay. And then what you are measuring here is now the distribution of those photons in that pixel array showing these 2 distinct Gaussian peaks. And so it's showing that even in that fine resolution, we can distinguish 2 peaks of emission photons that we might want to characterize. And so he would go through and essentially align up where you're going to count, because you don't want to count that, you want to count that. And so he would say, I'm going to count just these 2 or 3 pixels or whatever it is here, and collect those counts over the course of my measurement of that sample or all the different samples. And so you do that for each wavelength. It takes maybe 15 minutes. Where you look at what it look like, the distribution, peak shape, and set all those parameters so that you're actually measuring what you need to measure. And the skill set to do that is not huge, but it probably takes, it take a couple of days of training to get to the point where you really know how to navigate that, which is why it's not a huge barrier, but it's one that makes it more challenging to just walk in and turn off the street and do it yourself. Okay, so we're out of time now, so I'm going to stop. And I'll mention these 2 things on Friday. We'll start talking about mass spectrometry. So don't forget Friday, there'll be a quiz on some of these things which are really simple, and atomic absorption, largely, including neutron standards and so forth, on Friday. And then I'll see the rest of you today.
Question? Are we going to have lecture next Wednesday?
Yes. Well, are people going to be here? It's going to be empty.
All right.
Yeah.
Go ahead. No, I'm here.
I'll be here again.
Okay.
We'll be over that.